On behalf of the Sierra Foothills Amateur Radio Club, I want to thank everybody for joining tonight. It's a great turnout. Very much appreciated. Just a quick history on what this fifth Wednesday is about. On the first and the third Wednesday of every month on the W6EK repeater, we have an ElmerNet. And if you've never joined that, that's at 7:30. It usually runs for about an hour. So I would encourage people to check in on that if they're interested. And then on the off Wednesdays, with the ones we call the second and the fourth Wednesday, we have this Zoom meeting here, which is in the shack. And I would encourage people to join that as well. It's a lot of fun. It's a good in-face discussion on technical things, what you're doing, what you're building, maybe what you're purchasing, which is always hard on everybody's pocketbook, but it's a good thing to know. And then once in a while, like I mentioned earlier, we end up with this fifth Wednesday. And hams don't like to have empty time. So we figured out we'll do special presentations if we have them. So tonight we're going to have Dr. Ed Fong talk to us again. We had the pleasure of him talking to us earlier this year on J-pole antennas. Just some real quick items on Dr. Ed Fong. He was first licensed in 1968 under the call sign WN6IQN. When he upgraded to an extra later on, in that time he had to do CW to be upgraded. He moved to WB6IQN. He attained his bachelor's, his master's from the University of California at Berkeley. Go Bears. And his Ph.D. from the University of San Francisco. He's a life senior member of IEEE. I think a lot of you are familiar with IEEE. He has 12 patents to his name. Well, that is outstanding. And 40 published papers. He has books written on communications, integrated circuit design. Presently, he's employed by the University of California and practicing sounds like a lawyer. He's a professor at Santa Cruz. And he's teaching classes in RF design and high-speed interface design. During his 40 years career, he has also done work for Motorola, National Semiconductor, Phillips Semiconductor, and Advanced Micro Devices. So with that, I'm going to stop sharing. I'm going to thank you, Dr. Fong, again for the presentation tonight, and I'm going to turn it over to you.
Tonight, we're going to talk about this really cool transceiver I ran across, and quite by accident. We were sitting at a meeting at the Foothill Amateur Radio Club, and K3ADM agent says, "Hey, what do you know about this?" I knew nothing about it, actually. And, you know, for I think it was $150, $160, I said, "Why don't we buy one? It sounds like the specs look pretty good." So we bought one, and now it's become really, really popular. So we'll talk about it today. So we investigated. It's quite innovative. It's very, very innovative. So here's how it looks. It's very small. In fact, I'm holding it right here. It's about the size of a novel. Weighs 1 pound, 4 ounces. That's with a 4 ampere hour battery. It comes with a mic. And now if you buy it properly, it comes to the mic and a charger. They all don't come with the charger. And it's very hard to buy it with the battery. I get it through Ron Kwan. Now, John says you can also get it. It's tricky. The reason why is you can't get it with the lithium ion batteries. You're not supposed to send a lithium ion battery overseas across an airplane. So that's why it's hard. I think you get it locally here. They put it together. That's how they do it. But you're not supposed to, by law, send a lithium ion battery because of the fire hazard. It's 8 bands, so standard 80 through 10. It does not do 160, and it does all the work bands. It's a general coverage receive. It's an SDR radio. I'll show you in a while. The front looks like that. It's not very big. It's pretty cool. LCD. It's not a color screen. 2-roll screen. The back has got the mic input, push to talk, and a cat interface for FT8. And the key is buying it with the 4 ampere hour battery. It's hard to find, apparently, but you can find them. It fits right in the radio. It's a square battery. We bought the first one without the battery, and that was a mistake. So we kind of stuffed in 3 18650 batteries in there. They work, but try to get it with the battery. 4 ampere hour. This thing will last you all weekend. I've had it. It's lasted all weekend. It's ultra low power because it's using basically a microcontroller on transmit. We'll go through the transmit amplifier. Very efficient amplifier. That's a real innovative part about this. And this is it's an experimental radio. It works. I don't think it's ready for full commercial. Like ICOM wouldn't sell something like this. It's got some little bugs in it, but it's very usable. Here's the inside with the cover taken off. 1-inch speaker. Here's all the tuned circuits for the band. So 80, 40, 20, 60, 30, 17, 10, and 15. So those are the output and also input filters. What's interesting about this is the final output transmitter. Those 3 transistors are called BS170s or FETs, is the final output. And you figure, wow, where's the heat sink? Well, that's what we'll get into. It doesn't use a heat sink. It starts out as a Class E amplifier, it's a switching type amplifier, but it has to do a little bit more than that to generate single sideband. And we'll get into this in a while, how it does it. So the good thing is it's a switching, the 3 transistors gives you continuous about 3 to 5 watts. So it qualifies fully for QRP. Peak to peak, obviously a little higher, but it's very efficient switching. I'll show you the waveforms now. It's fully switching. So how do they generate single sideband? We'll get into this. And so there's a bunch of chips here. The heart of the radio, I think, here's the heart of the radio. It's an ATmeg, that's an Atmel chip, Atmel microcontroller chip, which they did not compile. It's done like an FPGA. They programmed all this in. And it's a really good chip in that it's got a PWM. It's really designed for audio processing almost. It's got a couple of PWM converters here. Like, for example, the audio, when they convert the 8 bits back into audio, there's a pulse width modulated converter, which then you can go through a low pass filter and drive a speaker. So it's really designed for that. And it's also got some, let's see, can you see the pulse width modulator out here? So it's got a pulse width modulator inside built in that you can control. It's not strictly a whole microprocessor type chip. It's really geared for audio or some type of signal processing. Because you write all this code, and I'm not a software guy, but apparently they've worked on this for years. Northern California DX Club, a group in Germany, Manny, DL2MAN's group has worked on this, and they put all this in a chip. And by the way, this chip, you can buy it from Jameco for about $2, $2.50, something like that. It's just not very expensive. It's fully programmable, but it's all on the software. You download the code that they'll give you free. It's open source that they've worked on for years and years and years. And let me tell you, this is amazing what this thing does. A bunch of attenuators. Of course, it needs an ADC. So you can tell it's got some analog actual attenuators in here, but then it goes to eventually an ADC, an analog to digital conversion. And it's a delta sigma converter, 192 kilohertz delta sigma converter. And then from there, it goes through filters, a bunch of Z transforms, again, more attenuators, Hilbert transform to generate the single sideband DMOD. What you're interested probably, here's the single sideband DMOD, AGC, of course. With the filters, it's got 100 hertz, 200 hertz, 1700, up to 4 kilohertz. So you can vary the bandwidth. You don't have to buy any filters, just like any new radio these days. And then eventually comes back to audio. Again, on the single sideband side, they do virtually similar ADC, a delta sigma ADC, going through a bunch of filters. And then of course they developed the INQ here. They don't show it here. INQ, the gain, and I guess here's the INQ equivalently to generate the single sideband. But then they have to, it's this clever algorithm of how they do the PWM on it. I'll show you this in a while. It's very cleverly done. I wouldn't know how to do the code. I sort of understand the concept of it, but it's pretty complicated. A lot of work that goes into this. And of course, then outside of the actual chip, you still have the receiver, an attenuator, a mixer. And then on the transmit, again, this is the tricky part. It's a PWM signal that goes into a Class E amplifier, which they convert what I call Class S amplifier. And the signal is generated by a Silicon Labs synthesizer chip. But it's a Silicon Labs synthesizer chip that we can control the rising edge and the falling edge. Well, I'll get into this in a while. It's very interesting how they did this, where then the actual class E amplifier is switched. But in a true class E amplifier, a true one, you don't modulate it. Here they do, and I'll show you how they did it. It's very, very, I think, extremely clever. But again, it all fits like this in here. So the thing that they couldn't integrate very well, of course, is the actual filters. The filters are still there. Well, that you can't integrate. But the final output, because of switching, doesn't draw power. It draws very, very little power. It's about, in the 40 meter, 80 meters, it's very efficient in the 80%, 80, high 80s for RF. That's extremely good. It's a little less in the 15, 10 meters, probably more like 70% efficient, but that's very efficient, very, very efficient for a single sideband amplifier. Much better than what you would get regularly. There's some disadvantages I'll show you in a while. So the radio is fairly small, and the battery fits right on top. The battery it comes with, that's really critical, get that battery. 4 ampere hour lithium ion just fits right on top the way they have it. Just barely gets in there, top closes, and lasts you all weekend. It'll last you all weekend. So I've done it. I've gone up to the hills here and put up a dipole antenna, and it's amazing. Anyway, so that's the basic diagram of it. And I can send you a copy of this talk if you want to do the details. I don't understand all the details. I know it works. Plus it's got a CW decode. They wrote an algorithm for CW decode, so it's a pretty good one. I don't think it's as good as what you can copy if you're a real good CW operator. If it's a good clean signal, it decodes fairly well. What it doesn't decode very well is a lot of QRM. If you have a lot of QRM, then you got to narrow down the filters and get it real clean. Otherwise, it gets confused. But it's pretty decent. So here's the Atmel chip. See, that's the heart of the radio. It's a whole microcomputer. Obviously, there's a bunch of memory or logic arrays that you can program. It's not very big. It uses a RISC architecture, so it's very, very quite fast, relatively fast, 20 megahertz clock. And it really isn't that sophisticated. 1 kilobit of EEPROM, 2 kilobits of static RAM. It does a lot of IOs, 23 general purpose IOs. And it doesn't cost very much by itself. It's a couple of dollars. So again, I was saying the radio weighs it's over a pound with the battery. It's the size of a novel. It'll fit right in a big pocket, 5 inches by 3.5 by 1 inch. It will run anywhere from 8 to 15 volts and run fairly well too. Do 5 watts, peak to peak, but under 10 watts for if you measure peak to peak. It's a built-in little 1-inch speaker, loud enough. Not super loud, but loud enough. And by the way, that's a switching amplifier. That's how efficient they are. That's a switcher they use in there, not a standard linear, because it's got the PWM demodulator. I measured on the receive about 90 milliamps, not bad. If you figure if it's got a 4 ampere hour battery, 90 milliamps, so it should go 40 hours. Continuous, it should go 40 hours. So a good weekend, if you're going on and off, good weekend. Again, when we measured pretty high efficiencies, we're talking in the lower bands, 80%, a little lower, and about 70%, 60% by the time you get to 15 to 10 meters. That's very, very efficient for an RF amplifier. It uses a very high precision TXCO, so it's fully qualifies for like FT8. And these days, these things are so cheap. It's amazing. You get 0.5 parts per million, or better. So it fully does FT8 really, really well. And here's the bands. Let's see, what else can I say about it? Again, built-in DSP filters. We used to, when we were growing up, I used Collins equipment. Filter running $150, $200. These days, it's all built in. It probably doesn't sound quite as smooth as a true mechanical, but not bad. Very usable, very usable. The noise reduction is built in. I'll use it once in a while. It's okay. The CW decoder, again, as good as they come. Again, if it's real noisy, not noisy, but QRM, a lot of interference, then your head, you probably can do better in your head if you're a good CW operator for sure. But if you're not familiar with CW and you hear a pretty clean signal, it decodes it quite well. I'm pretty impressed. So the volume control is not a pure volume control. It's actually a full attenuator. It's got a bunch of attenuators. The reason why is in DSP, you have to be very careful not to overload each stage. Right? If you overload a stage, it's garbage. It doesn't just sound distorted; it's garbage. So you got to make
Dr.
sure you
Fong,
yeah.
I have a couple questions here
Sure.
that are coming up as we do the chat here, trying to keep the noise limited. But one of them was, does the radio have sufficient frequency stability for whisper operation?
I don't know.
Oh, okay.
This is half a part per million is pretty stable. I mean, it's as good as any radio gets because they use a TCXO, state-of-the-art TCXO. So whatever ICOM or whatever those guys use, this is what they're using. So I would imagine it should be good enough. I know people have used it to FT8 and it works fine.
Yeah, it looks like we got some comments that they have used it for whisper, so it does appear to work for that.
Yeah, it's very stable. Half a ppm is very good, by the way. That's excellent. You know, 1 hertz per megahertz, or half of that. That's very stable compared to our old days with PTOs. That's really super stable.
Nice.
Let's see. Okay, so the most interesting thing, so this SDR, people have done these SDRs now. You can find various versions of it. So that's not absolutely new. They used a lot of code from other folks. By the way, I have nothing to do with this radio. I don't make it. I didn't have any designs. I'm just impressed with what they did. And when we bought one, I was just really intrigued of how it worked and how they managed to get this whole thing for about 100 shipped to your door. We get shipped to the door with battery, with charger, shipping, tax, $155. That I was impressed with that. And actually, I guess if you go through China, certain channels, you can probably get it cheaper than that. With the risk of losing it in the shipping. But if you can buy it here, you can about 155. Just make sure you get it with the battery and charger, because if you don't, it's almost impossible to find aftermarket. Let's see. I think the most interesting thing is the power amplifier. I mean, the other stuff has kind of been done before, but not this power amplifier. So it starts out as a class E, but it's actually what's called a class S, or sigma delta amplifier. S for sigma delta. They wanted a switching amplifier to do single sideband. That's unheard of, actually. I had never heard of this until I played with this, and I go, this thing works. So I started looking into it. Well, it turns out that delta sigmas have been around for 20, 30 years. That's what they do in audio. It's called an oversampling 1-bit converter. Max Hauser and Bob Broderson at Berkeley back in the 80s and 90s explored this, and they became well known for this technique of 1-bit delta sigmas. And I'll give a slight discussion of how that works. But the guy that applied this properly, the delta sigma, which if you buy like a CD player these days, it's a sigma delta type converter. But Andrew Semilak was the guy that did the Ph.D. dissertation on how do you apply this to RF. That is amazing. How do you apply the same principle so we can get these efficiencies at 40 meters, 20 meters, amplifiers, things like that. That's what he did. And his purpose, when I read his thesis, by the way, I can forward it to you. It's really complicated, very mathematical. His purpose was not ham radio. It doesn't even, I think his thesis doesn't even say he's a ham. It doesn't have to. But his purpose was to produce semi-analog signals in RF using the switching type technique, mainly for cell phones. Cell phones are, usually it's digitally modulated. So it's not true analog, but it has different levels, 8 levels, 16 levels. So it doesn't require pure linear, but it requires more than just a switcher. It's kind of in between. So he was trying to find, instead of using a linear amplifier to do ODFM type modulations, could we find a compromise, a switching one to get the efficiencies? And that's what his research is about. But I think these guys over at Northern California QRP Club, and Manny said, this is an interesting principle. I think we can use this for ham radio. Here's it. So Max Hauser and Bob Broderson did the 1-bit. Andrei Semilak applied it to RF. And so let's get into kind of what they do. And by the way, you can always go to these sites here. I don't always keep up with them. They're always updating. These guys are just really, really sharp guys. And Actually, I have a slide in the end of all the people that worked on this. They play around with this day and night. They even have a new version out called QMX. But see, so here is the kind of blurry. Here's the amplifier. So the final amplifier is just logic gates. Here's the 3 FETs I was talking about, those ones that don't have heat sinks. The 3 FETs, the BS170s. It's driven by a logic gate, a 7400 series, in fact. It's just a quad NAND gate. Right here, 74CT00, 7400 gate NAND, amplified twice. And so these are logic, so it'll be a square wave, but it's driven by this Silicon Labs PWM pulse width modulation chip. But the pulse width is a little trickier than you think to generate single sideband on this. So the whole idea is this is only logic levels, high and low, high and low. It switches the FETs high and low, high and low. So how do you in the end reconstruct it with the filtering to look like upper sideband, lower sideband, or AM? Yeah, that's pretty hard. But if you could do it though, you can get the efficiency out of these FETs. You're just switching them. It's where where transistors burn power is in the analog mode, right? In analog mode, you lose the efficiency because you draw current to ground. If you can put these in a switch mode, it's either on or off. And yeah, there's a little bit of leak through, but it's pretty efficient from the 80–90% region. So that's the basic schematic. Nothing tricky. It looks like just a switching amp, except it's how you, this signal generator here by Silicon Labs, how they generate that pulse, moving it back and forth very, very carefully. So here, you would think, in a sigma delta or a PWM amplifier, which you guys may have heard of, pulse width modulated amplifiers, they use them in audio, they use it in switching power supply amplifiers. Why can't you do that and produce an efficient amplifier at RF? Because these amplifiers have been around for years, and especially switching power supplies uses PWM. These are based on changing the pulse width, the actual width, depending, if the width is shorter, the voltage is lower if you reconstruct and integrate it. If the pulse is wider and if you rectify it and integrate it, the voltage is higher. But then what you see is the pulse varies quite a bit. And in order to do, and you can do this in audio and you can do this in a DC power supply because the frequencies are rather low, typically in the hundreds of kilohertz. So in hundreds of kilohertz, you would need a FET switches. Yeah, it's in the megahertz, right? If you look at delta signals, it's in the megahertz. So it's probably 10 times higher than the actual frequency you're operating at. In order to PWM it, you need the FET or bipolar. Mostly it's FETs now. And it's got to be 10 to 20 times faster than the actual switching frequency. Well, so if you calculate that, you can't quite do that for RF because by the time you get to 28 megahertz, you'll need FETs that switch at hundreds of megahertz. And maybe you can do it, but they would not be cheap. They would not be cheap if you thought you could do it that way. And you probably theoretically you could do it on a simulator if you get high-speed FETs, high power that you could switch. And they have some, but it's very limited. If you're going to get a few watts and try to switch a FET at hundreds of megahertz is pretty tough. So you can't quite do it that way. So Semilak comes up with an interesting idea. So, here's a good. See, here's a PWM signal, pulse width modulated amplifier. You see this in switching audio amps. You see this in power supplies. If you to scope it, it looks like this. So if you rectify this and put it through a filter, this would be low DC voltage. This would be higher, and this would be even higher, depending on the width. You pulse width modulated. Again, you would have to sample it very, very high if you were to generate a random type signal at RF, 10 megahertz, 30 megahertz to generate upper sideband, lower side, AM, whatever. If you use this technique, the FETs that you would need have to switch very, very fast, hundreds of megahertz to have low distortion. So you can't quite do this. You can't quite. So this is not practical for RF. You would need switching transistors, I don't know, gigahertz to be efficient, but it's hundreds of megahertz for sure. So, okay, I'm going to try to teach you some real quick about sigma delta type modulations. Again, you use this daily in your audio amps. They all have gone to sigma deltas, but how much of it does we really understand? I'm going to try to give you a 5-minute course in it. Okay, I'm going to try to convince you of this. You probably heard of Nyquist sample rates. In other words, I'll give you an example. On a telephone, a standard phone you would use, typically, the original spec was 4 kilohertz roll off, and these are real specs of these used. 4 kilohertz roll off. Nyquist is, in order to capture all of that, you would have to sample at 8 kilohertz minimum. 8 kilohertz absolute minimum. That's the law. I mean, usually you have to sample more, but minimum 8 kilohertz. And in your telephone, they have determined you need about 8 bits of resolution. Those vertical resolution. You have to have 8 bits, or in other words, about 2 to the 8th is about 256 levels. So that's about 0.5% distortion. That's what a telephone would give. You need about 8 bits. Any less than that, it'll be too much distortion. So the old phone system, it's a little bit more sophisticated. They use mu law compression to try to get rid of distortion. But in general, it's an 8-bit system. In an 8-bit system, 4 kilohertz, if you go by Nyquist, you would have to sample at 8 kilohertz. So 8 bits times 4 kilohertz, you would need 4 kilohertz sampling at 8 kilohertz to meet Nyquist. You would have to have about 64 kilobits per second. In other words, if you were to talk on your telephone in the old days, analog, and you wanted to convert that to digital, where you wanted to transmit that digital overseas or whatever because you didn't want to pick up noise, you would have to go to about 64 kilobits for you not to notice that, hey, you went digital. And for a while there, in the 1980s and 90s, that was 64 kilobits long distance calls. They sounded really good. You heard the delay, but they sounded really, really good because they were using 64 kilobits. Well, 64 kilobits, you can look at it another way. I can try to convince you of this. So in a phone conversation, 4 kilohertz, 8 bits of resolution, reasonable fidelity, you need to sample at 64 kilobits. And you might remember this when you guys had phone modems. You would get a maximum about 56 kilobits, the max. Right? You would phone in for your internet or whatever, and they'll show you what the data rate is. If it was really, really clear, really, really good line, you might get 53, 54 kilobits. That's about all you would get. Theoretically, you get 64, but they had some overhead bits, so that they took away some. So what was left to you is at best 50, 55 kilobits at best. So that's what you would need. So that has to stay constant. But here, I'm going to take a leap forward. This is what Max Hauser said. Now, but this is sampling at 8 kilohertz, 8 bits. What happens if I sample only at 7 bits? If I wanted to get the equivalent number of bits out of it, I would have to now sample, instead of at 8 kilohertz, I sample at 16 kilohertz. In other words, if I cut this down by 1 bit, and still keep everything, I have to sample it twice as fast. So in other words, if I went down to 6 bits, let's say, in order for us to maintain that fidelity or the information, I can't continue to sample at 8 kilohertz. You'll start hearing distortion. The math says you have to sample at 32 kilohertz. Well, let's go down another one. How about if I just have a 5-bit A to D and I want to maintain the voice quality of 4 kilohertz? Well, the math says then you have to sample at 64 kilohertz. But maybe you get the hang of it. Every time you lose a bit, if you don't want to lose any information, you got to sample twice as fast. So you just continue to go down. Well, what happens if I just sample 1 bit at a time? 1 bit level, not 8 bits. 8 bits is 2 to the 8th is 256 levels. 1 bit, it's either 0 or 1. How fast would I have to sample to get a telephone call through or telephone quality 4 kilohertz? You would have to sample at 1,024 kilobits. So as opposed to 64 kilobits, you have to sample at 1,024. So mathematically, that's what that says. If you want to go from 8 bits of sampling to 1 bit to not lose information, you would have to sample at 1,024 kilohertz. So that's what Max Hauser and Bob Brodesson's theory they worked on in the 80s and 90s. So why is it that you want to go down to 1 bit? Well, that's because microprocessors, memory, digital is all 0 or 1. What you've done is you've described an analog signal with zeros and ones only, zeros and ones. And the math says you can do it, but you would have to sample it at 1024 kilohertz. It would have to be much, much faster. If you were to do an analog, for example, 8 bits, then of course, if you go 8 bits, you can sample much slower. But that's what the math shows you. But again, the breakthrough is not 2 bits, it's 1 bit. Because at 1 bit, all digital stuff is 1 bit. It's not 2 bits, it's 1 bit. So when A to D converter is either 0 or 1. It's by definition 100% linear. It's either 0 or 1. See, if it was 2 bits, then you could have 0, 0, 0, 1, 1, 0, 1, 1. You can have 4 levels, which means they could be a little off on each one and they'll introduce distortion. But at 0 or 1, you don't have it. But what's the disadvantage? You got to sample really, really fast. So if I convince you of that, of course, there's been a lot of PhD dissertations done on this. I'm just trying to give you a 5-minute compact definition of this. So if I've convinced you of this, so, okay, I think I've talked to this exactly. This is exactly what a class S delta sigma amplifier does. So say, for example, we keep the fundamental, let's say 40 meters or 7 megahertz. You cannot vary that width much. If you pulse width modulate it, the math says, then you have to have a very, very high speed FET. Don't have that. So what can you do? What you do is, here's your 7.2 megahertz or 40 meter signal. You can't change this much. If you modulate it, it turns out you work out the math, you would have to have a higher frequency response FET. You can't move this very much, these edges. The square wave, how do you make that into AM, upper sideband, lower sideband? So the only thing you can do is move this edge back and forth or move this edge back and forth. Not very much, but I said not very much, but very fast. 800 kilohertz fast. Remember, your audio in ham, so 2.5 kilohertz. You have to correct it at 800 kilohertz at a time. Doesn't move very much, but it has to go back relatively fast. Not relative to the carrier, but relatively to the modulation frequency of your voice. Voice is 2 kilohertz, 2.5 kilohertz. You can move these edges. The way they do it is like this. And this is the fancy part I don't understand. This is all in the math. Your voice comes in here. You separate it. This is a sigma delta 1-bit modulator. And you determine how much you move the positive edge, and the negative edge. Or in other words, if you look at how much you can move this back and forth and how much you can move that back and forth. Now, again, how do you move it? I must admit, I do not understand it. Andrew Semlock goes through in the thesis. You got to program it in, and it's got to be done in real time, right? As you're talking in your mic, it's got to be positive edges, negative, positive edges, negative edges at 800 kilohertz per second. And you can go through all these transforms and it gets really complicated. But somehow he comes up with a solution that is algorithm, whatever it is, and I don't understand it, that when you talk into here, it will give you the proper edges to drive the positive edge and the proper edges to drive the negative edge. And when you combine it all back, you get this. Okay, this is what you get. This is what the square wave looks like before you filter it. Now, this is a continuous time. So on average, look at this thing. On average, it looks like a square wave. This is before the filtering. This is the output of the FETs before the filtering. A lot's going on here because this is, an average of all the signals. It's continuous. This is continuous. If you were to freeze it with like a storage scope, each wave would be a little bit different, a little bit different. Well, in this case, it's an AM signal. Here's then I chose 7.2 megahertz in the center. My spectrum analyzer, 7.2 megahertz. Here's an AM signal. It looks pretty good, actually. Here's the modulation with 2 kilohertz tone, right? There's a 2 kilohertz tone there. That's not bad. I agree. It isn't too bad. And if you talk into the microphone of this little radio here on AM, it sounds pretty decent. But how about single sideband? On single sideband now, I switched to single sideband, same mode. I put in a 2 kilohertz tone. 2 kilohertz because you know exactly where it's supposed to land at. So the carrier's here. It's got 20 dB of carrier rejection. Surprisingly, the other sideband rejects quite well, but it's a little noisy. You see this noise? It isn't smooth. So that's the 2 kilohertz tone, lower sideband. And here's the 2 kilohertz tone when I switch to upper sideband. And here's the middle at 7.2. And it leaves this residual noise or distortion. It's audible because this is 10 dB per division, so it's there. And it's there 15, 20 dB. It's 10 dB, 20 dB is 1%, so it's about 3 or 4% of distortion. And yeah, you notice it, but it's very usable. I mean, I make contacts on. I find that some guy in the net says buy the QRP kit's $15 microphone. I think if you soften the input, it's a little bit better in distortion. The mic it comes with is, I'm sure a lot of you guys have it. It's usable. This one's really, really good. It's much, much better. But here I was just stimulating it with a pure tone to the line level. Let's see what else. Yeah, here's the mic I like. It's $15. Someone suggested it. I think it does work quite well. Okay, so I had nothing to do with this project except that I just blown away of how it modulates and how efficient it is. The guys that are referenced to it, Andrew Samanek's Ph.D. dissertation, they did the power amplifier at the University of Erlangen in Germany. Again, Max Hauser, Robert Broderson, and principles of oversampling, A to D 1-bit converters. The guys that worked in the radio, the Northern California QRP Club, you guys probably know some of these. Dan Taylor's pretty well known. Manuel, DO2MAN's pretty well known. This guy's pretty well known. I don't know him. PN2NNZ. And yeah, so I think Steve Weber is very well known too as a power amplifier design. I don't know these guys personally. I've heard of them. Okay, so now I'm open for questions. Hope you guys have waited.
Yeah, I have a quick question. This is Graydon, KC6SLE.
Sure.
I've used this radio. I've been very impressed in what I've been able to do with it. I get good signal reports on it. The people that hear me on it give me good feedback on how I sound. So
really,
yeah,
I don't ask.
I have asked because I'm curious. But the one thing that annoys me on this radio is when you switch functions or you switch the controls in the front, you get a lot of noise. It's very noisy when it switches nodes and functions. I was just wondering if they're working on that on the software or they're working on that on maybe some hardware upgrades. Do you know?
No, I have no idea. Now, are you familiar? There's several manuals out there. Are you familiar with when you switch the bands that you hit the main switch real fast twice?
Yes.
Okay, you're familiar with that. And then also, if you want the volume control, you don't have to go to the menu. You hit the button in and then you turn it and it changes the volume.
Yeah.
So
okay. It does, you bring up a good point, Ed. It does take a while to intuitively learn what all the controls do and what they can do. And you find things. It's kind of like playing Mario Brothers, what's hidden in the cloud.
Right.
But
because it doesn't have very many buttons. It's only got 3 buttons in front.
Yes.
So it's got to be all menu driven.
And I don't know, Doug's out there, W2VX, I can talk to him about this too. It's just the harshness of the switching noise that is the only thing really annoys me on the radio. Other than that, it performs very, very well. And I've been impressed. I've made contacts throughout the United States on a QRP.
Yeah, I have too. I talked to Chili the other day on 15. I was amazed he could hear me.
Yeah.
I guess the key thing is having a good antenna, good resonant dipole high up in the air really makes a difference.
One day I broke into a net on the East Coast And they actually replied to me, and they were all bragging about how many hundreds of watts they were.
Right.
And they asked me what I was using, and I told them I think I'm putting out about 3 watts, and they almost called me a liar. So
What type of antenna are you using?
InFed.
Oh, really?
Yeah.
You're using my most unfavored antenna.
Yep. I know a lot of people don't like it, but it serves
I
me.
mean, it's convenient, right? It's definitely convenient.
It's convenient for my location, yes.
Yeah, all the tests I've done, the best antenna, if you could do it. You can, if you're going to go QRP, if you can do it, I'm not saying you can always do it, is a resonant dipole, obviously, as high up in the clear as possible. That's easier said than done.
Yeah, no, I agree with you. Anyway, I've taken enough time. I'll turn it over to other questions.
But it is a pretty fun radio, right? Oh, it didn't complain about distortion. I don't ask anymore because I know it's about 5%. But the good news is the new QMX. That's the new version they're working on. It's called QMX. If you guys are into this, they have it working and you can buy it. But what they don't have is they don't have the audio working. It will do CW. And the whole trick is, see, right now they're sampling at 800. I don't know if you guys notice this. I said they sample at 800 kilohertz. But you notice when I did the math, it's supposed to be about 1,000 or about 1,200. It's because the processor won't go fast enough. Supposedly, this QMX one uses a faster processor where they'll sample it at 1,000 kilohertz. So 20% faster. So the audio distortion should go down. The bad news is I hear they got the hardware, but they can't get the software working right. So supposedly they sell you the hardware now, and they said we should get the audio working, but that's 6 months ago. So this is really hard when you think about how hard it is to do. I mean, I kind of do this for a living, and I'm looking, that's amazing that you can do all the math like that in real time.
And they can't build the QMXs fast enough, Ed.
Well, they can't?
No.
But hey, do you have one?
I ordered one. The backlog is gigantic. I thought it'd be here months ago, but
isn't it amazing? They don't even have the audio working and people are buying it.
figured why not? It was published in QST.
I mean, haven't they kind of promised the audio single sideband for months now? John, what are you hearing?
Well, I've just been bugging them to ship me my radio. I mean,
Oh, okay.
I've been tempted to go back and just have them ship me the kit instead of the assembled product, but I'll wait.
I see one here from, by the way, this is KN6WQU. I see
Yeah, go
one.
ahead, Dan.
I see one here from QRP Labs.
That's exactly QMX from QRP Labs.
Yes, it's $95. Apparently it does CW and digital modes.
Right, but not single sideband yet.
No, not single sideband.
Yeah, I don't know enough about. All I know is the latest one with audio, and the latest complete one is what's called the USDX Plus, not the USDX, USDX Plus. There's also the USDX, the predecessor to this, which goes a little cheaper. I don't have one of those. I just have the Plus. And I have to say, for what it is, not bad. I mean, I have to admire them for how they do this, because I would have never thought about the algorithm of how to move the positive edges and the negative edges. I mean, I have no idea of how they write the algorithm. It's kind of, to me, pretty complicated to cancel out the sideband, cancel out the AM, because obviously the AM one looks really easy, because the math must be much simpler for AM. Because when you put this on AM, it sounds great. But single sideband, I would call it acceptable, but certainly it wouldn't be something ICOM or Kenwood would accept at this point. It would have to sample a lot faster than that. I mean, you got to get it down.
Question,
Yeah.
Carol, you said in your testing, you guys had done some harmonic testing, and then Ed, you had kind of downplayed, that measurement. So, if 30 dB is adequate.
Oh yeah.
I mean, I see a couple of us grimacing on that. Do you really feel that 30 dB is adequate?
You're only starting out with 2 watts. 30 dB is
Right.
1,000.
Right, but are you going to stay at 2 watts? I mean, I always.
Oh
see
no, you
everybody
cannot.
buying-
Oh, hang on here. It is not recommended that you put this through a linear amplifier.
Okay, so
No, you
there's
do
the
not put this through a
qualifier.
linear amplifier. No.
Okay, so you're not worrying about 30 dB because you're not being heard. Got it.
Right.
Got it.
You
Okay.
have to remember, If you have 1 watt at 30 dB is 1 milliwatt.
And 1 milliwatt can be heard around the world.
It could be, yeah.
Yeah.
But then you have your antenna, right?
I was just kind of curious why, if somebody said, oh, your second harmonic's only 30 dB down, I'd move on to the next radio. So thank you for that explanation.
I mean, what does your radio do it? Well, actually, by the second harmonic, your antenna usually doesn't resonate very well at the second harmonic.
Agreed.
So you also get attenuation there. Yeah, I mean, there's going to be second harmonic, but yeah, you definitely don't put this through an amplifier. It's not clean enough for an amplifier. No way. But by itself, it's pretty good. It's good enough. So who else has one of these radios that's tried it?
Well, a lot of us have it. Ed, in fact, the members of River City, Carol's part of that, and Sierra Foothills, a lot of us have bought it.
Yeah, what do you guys think?
I think it works great for a starter rig, and we're going to give 3 away at our Christmas party. And I'm hoping we'll get a Silicon Valley QSO party going on it one day.
We could. Oh, I check in quite often on the Triple H net and on 7190 at night. And, usually every night I can usually get back east. They'll hear me back east. But yeah, it's interesting about the distortion. If I don't ask, they don't say anything. But if you ask and it's a good clean signal, it's about 5% distortion, 5 to as much as 10 if you shout into the mic. And that's the level where most people can hear you. But again, it's intelligible. 10% is intelligible, but you could tell it's distorted.
Carol, KP4MD, did you have a question? You can unmute yourself if you like.
Sure. Yeah, I definitely heard the distortion. We had a few of us tested one on the air back on Monday, and we were listening to ourselves through the web SDR, and yeah, you could definitely tell it was 5 to 10% distortion, depending if you were yelling into the mic. And I guess the quality of the mic itself also contributes to that, if using the cheap mic that they send it with.
Terrible. The mic it comes with is terrible. But
yeah,
I like this one because then it uses the speaker. Just being able to have the speaker in front and you plug the mic in front is a lot more convenient. That little cheap Baofeng mic they have. It's worth the $15. Go buy the $15 at QRP kits.
Have you looked at the transmitted phase noise on this rig?
Oh, it's so lousy. It's like 25, 30 dB down. Right?
Okay, yeah, that's understandable for the price, but
it's not. You're not going to compare this to an ICOM or a Yaesu. It's not in that class, but it's a pretty fun radio to play with.
Ed, on the microphones, I used the microphone off of one of my Kenwood HTs, and it really cleaned it up quite a bit. I mean, I got better signal reports with that mic than the one it comes with. Yeah,
I think if it's smoother, the roll off, you don't hit it as hard. It's very sensitive to that. So yeah, I've tried different mics. I found that this one is what a guy recommended from EHAM, for $15, not bad.
Alan, AI3 Alpha has a question about how well it performs in CW mode.
I don't know. It hears well and it decodes well and has a built-in keyer, and it also has a built-in memory. I think 100 characters, 200 characters it can memorize. So I've never, to tell you the truth, I've never used it on CW.
Your group, has anybody at River City used it for CW, Carol?
I don't know. I would use it on CW. I'm a CW operator myself.
Yeah, KS6RT here. I use it on CW from time to time, and it's just fine. But it's really the antenna. For example, I've been toying around, Ed, with the AT100 as the tuner. I think you told me don't waste it because it's just going to burn up the power of the tuner, right?
Well, the problem with the wire tuners, the antenna starts after the tuner. And when you only got 2 or 3 watts, you don't want the antenna to start right after the tuner. You want the antenna to radiate at the resonant point, high up at 30, 40 feet.
Yep, going that route.
I mean, it will work. I mean, it's better than nothing. I've operated. I mean, I've got kilowatts at home, but I love this QRP thing, so I've been playing around with it. And I find that, boy, if you operate QRP, it really pays to have a resonant antenna, a real at a high point, where the resonance is at a high point. if it's at a low point where you're operating, you waste a lot of the power. You only got
Yeah,
two
for
sweet
sure.
spots.
I mean, the River City folks built a board for the Tuna Tin version 2.0. That was putting out a whole, I don't know, 400 milliwatts, Carol.
Yeah, about that much.
And I was talking up and down California on CW on 400 kilowatts, 400 milliwatts.
Oh, yeah. On CW, I mean, you can have a Pixie. I've made contacts on a Pixie. You have to remember, it's almost 10 times more efficient.
Mm-hmm.
Speaking of the Pixie, it's very susceptible. The Pixie itself is very susceptible to overload from nearby broadcast stations.
Yeah, you
How
got to make
does-
sure.
How does the uSDX work that way if with overload, front-end overload?
Oh, much better. It's got attenuators, and when it overloads, and you know that's why the volume control is not a volume control. It's an attenuator control. It attenuates all the whole line. Oh, you'll know if it overloads. You won't hear anything. You know, in an SDR radio, it's just gone.
Or you won't know anything because you don't hear anything.
Oh, depending on what the software does, right? It'll just squelch.
Yeah. Phil, KM6NFS has a question about the firmware user. Is the firmware user upgradable? And if so, has anyone gone through that process?
I'm too scared.
Right?
I just don't. I don't want to convert this into a doorstop.
Cricket, yeah.
Are other folks doing that though?
Yeah,
Has
it's scary
anyone
to
done
do
it?
that.
It is.
I'm with Ed. I haven't tried it.
Yeah, I figure I've got a working radio. Could it be better? Probably. But I've talked to Chile on it. I talk over the US. It seems to do what I wanted to do. You know what I would do? If they came out with better software, I would just buy a new radio. You know, at $150, I'll just buy the new version. Oh, Carol has a question about, the radio will cover it. Sure. The 60-meter band. But you're supposed to have it channelized, right? Technically.
Yes, right now it's channelized, but they're planning on expanding us on the channel 3 to cover 15 kilohertz.
Oh, the radio has a VFO. Now, this is what I've noticed, the guys that have. It will transmit, the filters, it'll go out of band slightly, but you do need the filters for each band. But to give you an idea of how much you can go off, it will receive on all the whole, from actually 1 megahertz to 30. But it will actually transmit on CB bands fairly well, I notice. So
And that was into a dummy load, right, Ed?
No, it actually wasn't. but the good news is since CB was AM, it does AM fairly well. So it will go down there, but around 26 it won't. Then the filters roll off too much.
It receives FM, and how can it do that through a 4 kilohertz wide filter?
I don't know. Yeah, it has an FM mode. Yeah, you got super ultra narrow band FM. I don't know. I don't know the details.
Yeah, it might be worthwhile tuning on the 10-meter FM frequencies and listening.
Yeah.
And see what it sounds like.
Yeah, because it goes through the audio section is only a 4 kilohertz FIR filters. I don't know.
Yeah, it is a lot of fun, and I'm looking at it right now. It has no type FCC type acceptance or labeling on it whatsoever.
That's because it's an experimental radio.
Exactly. So your operation on CB is okay.
I don't think so. I think you're supposed to experiment on ham bands only.
So I have two quick questions. This is Tom N6H. First off, you mentioned about adding extra FETs to it to increase the power. And also, can you increase the voltage to its maximum? I think it was 18 volts, and actually increase the power that way, or is it regulated on the board?
Oh, there's some regulation on the board, but the FETs are not. I wouldn't try that.
I tried it and burned up the finals.
You did, huh?
Yeah.
With the voltage or what? What did you do?
Well, you know what? There's a couple of controls that aren't really obvious in the menu system, and you have to make sure that you set those correctly so that you don't over burden and you don't heat those finals up. I'd have to go look at my notes, but there's more to it than once you get into it. Yeah, there's some settings that you have to know about.
There must be, because well, hang on, let me share again. Yeah, see, so there's the two sockets. So I did, come on, it's so enticing. I buy the BS170 FETs are very common for people that play around with RF. I stuck it in. Apparently, it's trickier than that because it did not increase the power. You have to retune it. Obviously, you're putting more capacitance. I don't know the details, but just by soldering an extra FET did not increase the power.
By the way, that footprint looks like a TO220 package. Anyone?
It is.
Anyone try a higher power FET?
The thing is, it's tuned to this. These stages is class E tuned. So that's why when I added the FET, I didn't see any difference.
Yeah, and you know what? Those BS170s are probably the best choice for that particular radio. There are some others that are similar, but that's really they're rated with a little more power.
Yeah, you figure these guys, if they built this whole radio, number one, I'd say they're not stupid. Number two, if it was obvious, they would have done it, right?
Yeah.
So again, I added the FET, it didn't make any difference. I was hoping it would add power, but because you're changing the tuning, all these outputs filters go into those FETs at the output of the drain. So if you added the capacitance of the extra FET, you would have to reduce it on all the rest. You have to retune it. So
well, I think the advantage, Ed, is that if you put in the fourth one, you don't get more power, but you distribute the load because they're all running in parallel, and so they may not get as hot.
They don't get hot to begin with now.
Burn some up.
But what were you doing?
Apparently the wrong thing.
Yeah, I mean, with the internal battery, I haven't been able to burn it up.
Hey, Dan, KN6WQU, didn't you treat yours as a George Foreman?
Yes, sir.
What's a George Foreman?
So it was putting out, I think it 8 watts for a good 3 seconds, and it was done. Yeah.
How many volts did you have on VDD?
13.5.
Now, how did you just overdrove it, or what were you doing?
That's correct.
Ah.
We guess Dan FT8.
Yes.
Nice.
Luckily, the FETs are cheap. You need some? I bought a dozen. They're cheap.
Yeah.
Yes, I played with it. I couldn't easily get it. So here's my settings. Here's what my settings are: noise gating 4, transmit drive 4, PA bias minimum 8, PA bias maximum 180. That's based on distortion. That's based on the spectrum analyzer putting in the 2 kilohertz song. Because I know the worst part of this is the distortion. Those are the settings I found that gave you the best distortion. Maybe not the best power output or whatever, but the best distortion. And it's still there, but it's acceptable.
Ed, another excellent presentation. I want to thank you for taking the time.
You're welcome.
Thank you so much. I loved it.